Hi guys, it's Mrs. Moss here, and we're going to continue our discussion on astronomy with looking at the planetary motions and the way we move in outer space. So if you look at these two diagrams, you see one is a picture of revolution around the sun and the other is a picture of rotation on our axis. We're going to look at this a little more closely. Are we moving? Well, the answer, of course, is yes. And the definition of rotation is when an object spins around on an imaginary axis. The period of rotation is the time that it takes for a planet to spin in that 360-degree circle. The rate of rotation for our planet is 15 degrees per hour. This is familiar to you. Hopefully you remember this from when we spoke about this earlier in the year. Now, the definition of revolution is when one object moves around another object in a definite path called an orbit. And the period of revolution is the amount of time that it takes a planet to complete one orbit around the sun. And our rate of revolution is 1 degree per day. So how exactly do we revolve, or how do we go around the sun? Well, a planet's orbit is the result of two opposing forces on the planet. It's forces of inertia and the forces of gravity. Now, let's look at this a little more closely. Inertia is the law that states that an object at rest will stay at rest, and an object in motion will stay in motion until an outside force is acted upon it. So in this diagram, there's a picture of a mass revolving around another mass. Mass 2 is revolving around mass 1. So if you notice, mass 2, with the law of inertia, if it did not have anything else to act upon it as it circled around, it would actually keep going straight. But because we have gravity that forces it from mass 1, the gravity helps to pull it in the direction around it so that it acts upon each other. One opposes the other. So let's look at what gravity is. It is a force and it pulls an object towards another. And the force of gravity is dependent on the mass of the object and the distance from that object. As mass increases, the force of gravity will also increase, making this a direct relationship. As the distance increases, the force of gravity will decrease, so that would be an indirect relationship. And in other words, if two objects are close together, then the gravity will pull one another. If the objects are far away from each other, then the gravity does not act upon it as strongly, and it's less of a force being pulled. So what does this have to do with our orbit around the sun? Well, inertia and gravity of the orbit is a compromise. It's between the sun and the earth. So gravity pulls the earth towards the sun, and inertia is what keeps it going in its circular or elliptical orbit. So inertia keeps Earth moving, and gravity holds the Earth in its orbit. When these two opposing forces are balanced, the result is a steady orbital path, and that's known as dynamic equilibrium. We've heard of this term too when we were talking about landscapes. We have erosional forces and we have leveling forces. When they are balanced, we call that dynamic equilibrium. Same thing here. When we have gravity forcing on being pulled on an object and we have inertia acting on that same object, it becomes balanced when those two opposing forces are steady. So let's talk more about how we know that the Earth revolves. We discussed the heliocentric model and Copernicus, who created this heliocentric model that we know of today, and how the Earth revolves around the sun, as do the other planets. But how do we know? Let's look into this a little bit. We have some proof. We have the changing of the seasons, right? And the seasons are caused by tilt of Earth on its axis and its revolution around the sun. Now I need you to write all this down. The seasons have nothing to do with the Earth's distance from the sun. It has to do with the Earth's tilt and with the way it revolves around the sun at the same time. But it does not involve a distance of how far or how close it is to the sun. If Earth was stationary or in the geocentric model, then the same part of the Earth would always tilt towards the sun, and we would have no changes in our seasons. So we know that because we have changes in our seasons in the most locations on Earth, that the Earth does revolve around the sun. So it's not just the tilt alone, it does have to do with the revolution of the Earth around the sun. The other piece of proof that we have that we are revolving around the sun has to do with the constellations that we see in the night sky. And the constellations are a grouping of stars and they form certain shapes. And that's what we call a constellation. So they change throughout the year, and that's because that we know that because our Earth is revolving around the sun. So every time we go around the sun, we're facing a different portion of the sky. So this is a map of some of the constellations that we can see any time of the year in our skies. And you'll notice that it actually corresponds with the horoscopes. Now let's talk about how the Earth rotates and proof that we have that the Earth is rotating on its axis at 15 hours at 15 degrees every hour. We have what's called the Foucault pendulum to help us with this, and it's named after Jean-Pierre Foucault. And you see his Foucault pendulum right here. A pendulum is a swinging object suspended high over the ground, and it swings back and forth in the same direction all day. And what Foucault discovered is that if you set up certain pegs in a circle around the pendulum, as the Earth rotates every hour, different pegs get knocked over from this swinging pendulum. So here's a picture of the Foucault pendulum in an observatory in Paris. Now it's not an easy thing to notice in the left picture. And if you look at the right picture, we have the pegs standing up over here, and you have the pendulum ball swinging. So as it swings, it will knock down the pegs. Well, in the course of 24 hours, all of those pegs get knocked down. And the only explanation for that is that the Earth is rotating, proving the same thing. So as a pendulum swings back and forth, it appears to change direction because the Earth has rotated beneath it. In reality, the pendulum does not change direction. Due to inertia, the pendulum continues to swing in its original direction, and with the law of inertia, we know that unless another force is acted upon it, it's going to continue swinging in the same direction. It only appears to change directions because the rest of the floor underneath it is rotating, because the Earth is rotating. Another way we know that the Earth is rotating is due to the Coriolis effect. And the Coriolis effect we've spoken about briefly when we talked about planetary winds. Now, on a non-rotating Earth, if the Earth was not rotating, a rocket would travel straight, that's traveling straight, would go straight. It would hit its target. So it would just appear to be moving straight. However, in life, this is not what happens because the Earth is rotating. When we have what's called the Coriolis in effect, as the straight rocket is shot out, it actually gets deflected to the right in the northern hemisphere and to the left in the southern hemisphere. So here's a picture of all the different routes of deflection. In the north, you notice that every arrow is pointed to the right, whether you're standing facing the North Pole, whether you're standing at the North Pole and facing the equator, it all moves to the right. In the southern hemisphere, it's the opposite. Depending on where you're standing, the Coriolis effect will make things appear to move to the left. So whether you're standing facing the South Pole, it'll move to the left, or whether you're facing the equator, object will move to the left. Actually, this is very significant. If you're a pilot, especially, and you're flying a plane, you do need to be aware of the Coriolis effect because it will alter your path. All moving materials traveling across the Earth's surface appear to be deflected off their straight line path. This predictable motion is due to the rotation of the Earth beneath it. The objects are traveling in a straight line path, however, they appear to be deflected because the Earth has rotated beneath it. The deflection is to the right in the northern hemisphere and to the left in the southern hemisphere, as I just showed you. Now, the third piece of evidence that we have that the Earth is rotating are called star paths. Stars, including the sun, appear to rise in the east and set in the west. So we have an apparent path, which we talked about when we learned more about seasons and the celestial sphere. The stars appear to circle around Polaris. Polaris is located at the end of the Little Dipper, right above the North Pole. And stars appear to move at 15 degrees per hour, which is the Earth's rate of rotation. So I'll show you a picture of what we consider star paths. And if you look, it's literally circles drawn around a center star. And that center star is Polaris, and we see tracks or star trails. This is a picture of it taken from a camera with a shutter that has been open for a very long time. So it collects all of the light during that time. And you see these lines in the sky. These lines in the sky are stars. And it's looking as if stars are moving because the Earth is actually moving. That camera is moving at the rate that the Earth is rotating, and it makes the appearance of the stars to have a trail. It's actually kind of beautiful if you think about it. Here's another picture, and if you look, the center star right here will be considered Polaris because that's located above the Earth's axis, out way, 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 way far away, but it is located at the right above the North Pole. So we always have this central star, and then the paths of the stars go around that, and it looks like it creates these cool trails. So we're going to end here for now. I hope you got all those notes down, and we'll see you next time.